Okay. And this is a video again on polynomial equation. Now this has happened to me more than one occasion when I'm trying to find a solution to one particular problem. Somewhat incidentally or accident, I won't say inadvertently, it just happens that I discover the solution to another problem. Now you can see from the expression that I'm using what that problem is. It has to do with trying to compactly code information. If you've seen any of my earlier videos, you will know that there is very little difference, both contrasting and similarity, between coding information for the purposes of error detection and correction as well as coding information for the purposes of data compression. Both of them are somewhat similar, but at the same time also the exact opposite. So this is this thing here. So we start off like this. Actually what happens is, let's consider the expression, let's say n plus x. This I'm starting off with, we all know the solution to the quadratic equation. We're looking for higher order equations. This method of solving problems, you can see that it can be used for if you can solve a cubic equation, we can use that method to solve the fourth degree or biquadratic equation and so on. If we know the solution to the fourth one, we can solve for the fifth degree and so on. So n plus x the whole cube minus n the whole cube is equal to m. Okay. If I expand this, I'll have n cube plus x cube plus 3n x square plus 3n square x minus n cube is equal to m. Okay. Now we have something like a cubic equations here, right? Involving x, so x cube three n x square plus 3n square x minus m is equal to 0. Fine. Now what I do is, so this is the equation here. So I took m as, since I wanted to, initially my substitution was x equal to m power 1 by 3, but now I changed it to x equal to m by c whole power 1 by 3. Okay, you can substitute that here. Okay, well, if we substitute that here, once we substitute that here, we will get the following equation: m by c plus 3n m by c power 2 by 3 plus 3n square m by c whole power 1 by 3 minus m equal to 0. Okay. This form of for solving it is based on the fact that if two polynomials are equal, that if and only if their respective coefficients are equal. Now we don't know what n is. Now I've taken this here. Okay. Okay, now you can just do this. I'll take let me take y is equal to another variable. Y is equal to m power 1 by 3 and c dash variable is equal to c power 1 by 3. Okay. Okay, this will mean m is equal to y cube. Okay. Now, after doing that, cross multiplying and all that, you will get the following equation: c dash minus 1 times y cube minus 3n y square c dash y square minus 3n square c dash square y is equal to 0. Okay. Yeah. I write the equation again. You will get c dash minus 1 y cube minus 3n c dash y square minus 3n square 3 3n square c dash square y is equal to 0. This is what you will get upon simplifying that, making that substitution. You can take out y here as a factor, and so you will be left with c minus 1 y square minus 3n c dash y minus 3 n square c dash square equal to 0. Here this will be c dash minus 1. Okay, so this is just a quadratic equation in y, and you can solve this, right? So you can solve for y, and we have taken y is equal to m power 1 by 3 and c dash equal to c power 1 by 3, right? So this is the solution for this thing. Now let us look at that original equation again and compare it with a general cubic equation so that we can just equate the coefficients. So this method is based only on that. The original equation was x cubed plus 3n x square plus 3n square x minus m is equal to 0. Right? So now we compare this with, I will write this as the general form of the cubic equation, which is x cubed plus b by a x square plus c by a x plus d by a is equal to 0. Okay? Okay, let b by a equal to b dash c by a, or rather let a by a, b by a equal to f c by a equal to g and b by a equal to h. Okay? Now we compare these two equations. We can always equate f is equal to 3n, c by g is equal to 3n square, h is equal to minus m. Right? And we know the solution to this equation. We just found out the quadratic, or two solutions we already know because we have solved for the quadratic equation. So we can factor out those two, we'll be left with the third one. Right? So we can equate these two. And so we just have to, this will give us clearly what the solution for it. We can generally solve any cubic equation this way. This can also be generalized to higher order, fourth and fifth and so on, as follows. But the only thing you have to do here is, for the cubic case, I assumed a constant m here. For the biquadratic case, you will have to assume a linear expression on the right side instead of a constant m. Because you have only two unknowns and you have the number of coefficients is more and more, all of them will never equate. So if you have to equate, you will have to introduce more number of constants into it. So you'll have to assume a linear equation there, right? So let us take n plus x power, this is for the biquadratic case, minus m power 4 is equal to L times x plus m. Okay. So doing all of that same thing again, you will come up with this equation: x power 4 plus 6 n square, sorry, plus 4 n x cube plus 6 n square x square plus 4n cube minus L times x minus m equal to 0. Okay. Right. Now again making the same, this thing only, same form of substitution only. Okay. Where I make, say, y is equal to m power 1 by 4 and c dash equal to c power 1 by 4. First I begin by taking x is equal to m power m by c whole power 1 by 4. Okay. And then, so we'll come up with the following equation here for the biquadratic case. Basically, we'll x dash power 4 into c dash minus 1 plus 4 n c dash x cube plus 6 n square c dash square x square plus 4 n cube minus L c dash cube x is equal to 0. Okay. Again, sorry, x dash here, not x cube, x dash cube, x dash square, and x dash cube here. Okay, if you take x dash outside, okay, instead of y for the cubic case, I'm using x dash here. because you don't confuse y equal to f of x with that. So x dash cube times c dash, you can have c dash minus 1 times x dash cube plus 4 and c dash x dash square plus 6 n square c dash x plus 4n cube minus l times c dash equal to 0. This is a cubic equation. From the previous method you can solve the cubic equation. So we can solve the biquadratic equation this way. This cubic equation can be solved because we just saw how to solve the cubic equation. Okay? So this gives you the solution for the cubic equation. So now again we look at the general form for the right. The general form for it is x power 4 plus 4 n x cube plus 6 n square x square plus 4 n cube x minus m equal to 0, right? I mean, assuming that the general form, the leading coefficient, you have divided all the other coefficients by the leading coefficient. The general form of this would be x power 4 plus f times x cube plus g times x square plus h times x plus I is equal to 0. Since we have the general form of the equation is I have made a mistake there. X power 4 plus four n x cube plus 6 n square x square plus 4 n cube minus L times x minus m equal to 0. Okay, so this is the form that we got initially when we did n plus x power 4. So these are the coefficients there, right? So we can equate them. We will get f is equal to 4 times n, g is equal to 6 times n square, h is equal to 4n cube minus l, and I is equal to minus m. Okay, since these two polynomials are equal if and only if their coefficients are equal, so we can determine n as and l as we need here, since we have enough number of. If you have to go to a fifth degree equation, you have to use a quadratic on the right side rather than a linear, so that you will introduce one more constant in the second and the linear and the final, so you will be able to equate more. So you will be able to determine constants as you need and use this general method that you have used to solve all polynomials.